Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
Here is the essay, Guillaume de l-Hôpital's analysis of infinitely small quantities for the understanding of curved lines, published in 1696, stands as a pivotal text in the early development of calculus. This essay undertakes a comprehensive evaluation of the internal claims, arguments, and specific content presented within that work. It scrutinizes the logical coherence, evidentiary basis, and conceptual frameworks inherent in l-Hôpital's systematic exploration of infinitesimal calculus. This analysis delves into the specific sections of his treatise, assessing the validity and limitations of his approaches through a careful examination of his mathematical reasoning. Section 1: Preface and Introductory Notions. The preface to l-Hôpital's analysis establishes its pedagogical purpose to elucidate the intricacies of the new calculus for a wider audience. The work, according to l-Hôpital, draws heavily upon the insights of Gottfried Wilhelm Leibniz and Johann Bernoulli. An initial claim is the accessibility of calculus through a structured presentation of its principles. Further, l-Hôpital emphasizes the power of this new method in solving problems related to curved lines, a domain traditionally addressed through more cumbersome geometric techniques. He lays claim to presenting a clear path for understanding fluxions and differentials. Evaluating this claim requires close attention to the subsequent definitions and propositions presented in the body of the work. The introductory notions, including the definition of infinitely small quantities as incomparably smaller than ordinary quantities, set the stage. This conception, while intuitive, lacks the modern rigor of epsilon delta definitions. It serves as an operational definition, allowing for manipulations without a fully formalized foundation. l-Hôpital's assertion that these infinitely small quantities can be discarded without affecting the accuracy of results requires a careful assessment of specific applications. The preface promises a practical gain thus. The subsequent sections must be examined to determine the real one of this. Section 2: Rules for finding differentials. This section deals specifically with the rules for the determination of differential quantities for different functions. Central to this section is the claim that finding differentials, the infinitely small changes in variables, is a systematic process governed by well-defined rules. l-Hôpital presents rules for differentiating constants, variables, sums, differences, products, quotients and powers. These rules are essentially equivalent to those found in modern calculus textbooks, yet their justification rests on the aforementioned notion of infinitely small quantities. For example, the rule for differentiating a product, given by the differential of quantity A times quantity B equaling quantity A times the differential of quantity B plus quantity B times the differential of quantity A, is presented without a formal proof utilizing limits. Instead, it relies on algebraic manipulation and the discarding of higher-order infinitesimals. The validity of this approach, within the context of its time, stems from the practical success of its application. l-Hôpital illustrates the rules with examples involving algebraic functions. The power rule, presented for integer and rational exponents, demonstrates the generality of the method. A careful evaluation of these examples reveals the implicit assumption of differentiability, a concept not explicitly addressed. Furthermore, the section presents rules for finding differentials of composite functions, essentially the chain rule. Though it lacks that formal nomenclature, his method centers around successive substitutions to find the relations of dependent differentials. The section's value lies in its codification of differentiation techniques, streamlining a process that had previously relied on geometric intuition. Section 3: Applications of first-order differentials to tangents, maxima and minima. l-Hôpital transitions from the calculation of differentials to their application in geometric problems. This section focuses on the determination of tangents to curves and the finding of maximum and minimum values of functions. The core claim here is that differential calculus provides a powerful tool for solving problems of tangents and extrema, surpassing traditional geometric methods in efficiency and generality. Tangents are found by considering the ratio of differentials representing the slope of the tangent line. The method relies on the concept of a curve being locally linear, which is expressed through infinitesimal analysis. l-Hôpital provides examples of finding tangents to various curves, including conic sections and more complex algebraic curves. The section demonstrates the power of the method in handling implicit functions where the relationship between variables is not explicitly given. The procedure for finding maxima and minima involves setting the differential of the function equal to 0, identifying points where the tangent line is horizontal. l-Hôpital acknowledges the need to examine higher-order differentials to distinguish between maxima, minima, and inflection points, introducing the concept of concavity, though without explicit terminology. The section offers examples with polynomials and more complex functions. The determination of maxima and minima hinges on the assumption of a continuous derivative, and smoothness of the curve discontinuities or singularities are not explicitly considered. The success of the method in solving a wide array of problems solidifies the initial claim, although a deeper mathematical treatment is required. Section 4 rules for finding the points of inflection and the cusps of curves. This section presents rules for determining points of inflection and cusps on curves. l-Hôpital here claims that calculus provides the necessary tools to precisely locate these singular points, inflection points, where the concavity of a curve changes, are identified by examining the second differential or second derivative. The rule states that at an inflection point, this second differential must be equal to 0 or infinite. l-Hôpital offers examples illustrating the method, including the analysis of cubic curves and other algebraic functions. He acknowledges that setting the second differential to 0 is a necessary, but not sufficient condition, requiring further investigation to confirm a change in concavity. Cusps, where the curve has a sharp point, are characterized by the tangent line being undefined or changing direction abruptly. l-Hôpital describes different types of cusps and provides methods for identifying them, often involving the analysis of the ratios of differentials. His approach lacks formal definitions involving limits, but relies on analyzing the behavior of the curve in the immediate vicinity of the cusp. The descriptions of different types of cusps contain the implicit understanding of what would later develop as topological concepts. The examples provided showcase the method's applicability to a variety of curves exhibiting these features. This section strengthens the argument for the utility of calculus in analyzing the qualitative behavior of curves. Section 5, concerning the nature of curvature evolutes and radii of curvature. Here, l-Hôpital delves into the nature of curvature, introducing the concepts of evolutes and radii of curvature. The main claim is that differential calculus provides a precise framework for quantifying and analyzing the curvature of curves. The radius of curvature at a point represents the radius of the circle that best approximates the curve at that point. l-Hôpital derives a formula for calculating the radius of curvature using differentials of the curve's coordinates. This formula is equivalent to the modern formula, but is expressed in terms of differentials instead of derivatives. Evolutes are defined as the locus of the centers of curvature of a given curve. l-Hôpital presents a method for finding the equation of the evolute by eliminating the parameters from the equations relating the coordinates of the original curve and its center of curvature. The calculation of evolutes involves finding the intersections of consecutive normals, essentially the normals at infinitesimally close points on the curve. These constructions demonstrate the power of infinitesimal reasoning in geometric contexts. Demonstrations are given for finding evolutes of parabolas, ellipses, and hyperbolas, showcasing the method's versatility. The section provides a rigorous approach to understanding curvature. The construction of evolutes through infinitesimal analysis demonstrates our precursor to modern differential geometry. Section 6 on the description and construction of curves. This section deals with the description and construction of curves, emphasizing the use of calculus in understanding their properties and facilitating their geometric realization, l-Hôpital asserts that calculus provides powerful tools for analyzing curves defined by various geometric conditions or equations, enabling their accurate construction. He discusses how to determine the equation of a curve given specific geometric constraints, such as passing through certain points, having particular tangents, or satisfying certain area or arc length conditions. The methods involve the setting up and solution of differential equations. Though the terminology of differential equation is absent, he illustrates the techniques with examples involving the construction of curves with specified properties. l-Hôpital addresses the problem of quadrature, finding the area under a curve, by relating it to the problem of finding the tangent to a related curve. This connection demonstrates the inverse relationship between differentiation and integration, though without a formal statement of the fundamental theorem of calculus. He presents methods for rectifying curves, finding their arc length, by expressing the arc length as an integral involving differentials. His work provides a glimpse into the early stages of geometric modelling through calculus. Section 7 Maxima and minima problems applied to geometry. l-Hôpital extends the application of maxima and minima to geometric problems, focusing on finding the maximum or minimum values of geometric quantities subject to certain constraints. The central claim is that calculus provides a systematic approach to optimizing geometric figures. He presents problems involving finding the maximum area of a rectangle inscribed in a triangle, the minimum distance from a point to a curve, and the maximum volume of a solid formed by rotating a curve about an axis. These problems are solved by expressing the geometric quantity to be optimized as a function of one or more variables, then finding the values of these variables, and make the differential of the function equal to 0. l-Hôpital addresses isoprometric problems, finding the curve of a given length that encloses the maximum area. This touches upon the calculus of variations, a field that would later develop into a sophisticated branch of analysis. His treatment of these problems showcases the power of calculus in solving optimization problems beyond purely algebraic or analytic contexts. This section highlights the application of calculus to geometric optimization, anticipating the more advanced developments in optimal control and variational calculus. Section 8 Singular points and their identification through calculus. This section presents a compilation of methods for addressing multiple forms of singularities and special points of curves, focusing on precise identification. Through the utilization of fluxions and differentials, l-Hôpital makes the claim that various features of a curve can be known through the manipulation of its differentials, including its concavity, points of inflection, and points of tangency. This is shown through a number of examples, including spirals and cycloids. Points of maximum and minimum are presented once again, now directly in the context of geometric problems. In this section, l-Hôpital seems to have synthesized the previous chapters into geometric analyses, which are then used to further motivate the utility of the infinitesimal calc. Section 9 dealing with curves defined by mechanical means. The 9th section turns to curves defined by mechanical means that would be difficult to express as algebraic functions. l-Hôpital argues that his theory finds utility even when curves are defined by mechanical processes rather than explicit algebraic equations. He examines curves generated by the rolling of one curve along another, such as cycloids and epicycloids. He also considers curves defined by linkages or other mechanical devices. The analysis involves using kinematic arguments, relating the velocities and accelerations of different parts of the mechanism, expressing these relationships in terms of differentials. l-Hôpital demonstrates how to find tangents, normals, and other geometric properties of these mechanically generated curves using calculus. His work in this area anticipates the later development of kinematics and mechanisms as a branch of engineering. The inclusion of mechanically defined curves expands the scope of calculus and demonstrates its utility in the analysis of physical systems. Section 10. The solution of indeterminate equations. This pivotal section tackles the solution of indeterminate equations, showcasing a powerful application of differential calculus to problems that would later become central to mathematical analysis. l-Hôpital's primary assertion is that calculus offers a systematic method for evaluating expressions take on indeterminate forms, such as 0 divided by 0 or infinity divided by infinity. He introduces what is now known as l-Hôpital's rule, stating that the limit of a quotient of two functions, as the variable approaches a certain value where both functions tend to 0 or infinity, equals the limit of the quotient of their derivatives. This rule provides a technique for resolving indeterminate forms that arise in limits, enabling the evaluation of expressions that will otherwise be undefined. l-Hôpital illustrates the rule with numerous examples, demonstrating its application to various algebraic and transcendental functions. He considers cases where the rule needs to be applied repeatedly to obtain a determinate result, which leads to higher-order manipulations. The section on indeterminate equations demonstrates the power of calculus in extending the realm of solvable problems. It highlights the crucial role of limits in defining and evaluating expressions in calculus. Section 11 on the use of differentials in finding the properties of series. In this section, l-Hôpital describes the utility of calculus in the analysis of infinite series. Here, the claim is that the infinitesimal calculus can be marshalled to determine the properties of infinite series, including their convergence and rates. l-Hôpital details the methods in his arsenal, including the ratio test and integral tests to determine the convergence of infinite series. The analysis of series extends the reach of calculus beyond the realm of geometric curves and algebraic functions. It demonstrates the power of calculus in analyzing infinite processes and approximating functions using infinite sums. Section 12 Further applications of calculus to rectification and quadrature. This final section expands upon previous themes, presenting additional applications of calculus to the problems of rectification, finding arc lengths, and quadrature, finding areas under curves. l-Hôpital here claims that calculus offers a versatile and powerful tool for solving a wide range of geometric problems. He presents examples involving curves defined by transcendental functions, showcasing the method's ability to handle problems beyond the realm of algebraic curves. He discusses methods for approximating arc lengths and areas using numerical techniques. He also touches upon the problem of surface area of solids of revolution. This final section reinforces the central theme: calculus provides a systematic and efficient approach to solving geometric problems. The presentation of diverse applications underscores the versatility of calculus and its potential for further development. In conclusion, Guillaume de l-Hôpital's analysis of infinitely small quantities presents a coherent and systematic introduction to the principles and applications of differential calculus. This work, while lacking the formal rigor of modern treatments, effectively conveys the power and utility of the new methods for solving problems related to curves, tangents, maxima, minima, and other geometric properties. The section Leistchen analysis reveals both the strengths and limitations inherent in l-Hôpital's approach. His reliance on intuitive notions of infinitesimals, lacking rigorous definitions, is balanced by the practical success of his methods in solving a wide range of problems. The systematic presentation of differentiation rules and their application to geometric problems provides a valuable resource for students learning calculus. The work's enduring significance lies in its role as a highly influential textbook that disseminated the ideas of Leibniz and Bernoulli to a wider audience, contributing significantly to the rapid development and acceptance of calculus as a fundamental tool in mathematics and science. The very accessibility that l-Hôpital championed, while occasionally sacrificing rigor, catalyzed the widespread adoption of calculus and its transformative impact across numerous disciplines.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.